Good afternoon, everyone. I'm Chao from the Hong Kong Polytechnic University. Now I'm happy to present the latest research progress from our team, which focus on the electrified vehicle energy management through the competence-aware reinforcement learning. In this presentation, I will cover four main aspects: introduction to the research background, formulation of the research problem, development of our methodology, and demonstration of our validation results. So according to the International Energy Agency's report for 2022, the global carbon emission scenario remains critical, with the transportation sector, including automobiles, accounting for 9% of emissions. Against this backdrop, the development of electrified vehicles play a crucial role in reducing carbon emissions and enhancing environmental sustainability. However, one challenge for electrified vehicles is their lower energy density. Therefore, improving energy efficiency remains an important topic in their application. Many electrified vehicles adopt hybrid energy storage systems, such as combining fuel cell engine with lithium batteries, to overcome the range limitations. The fuel cell engine supplements the lithium battery's endurance. For such vehicles, optimizing energy distribution among the multiple storage components to enhance overall energy efficiency is a challenge task, typically managed by the energy management system. We also call it EMS. Currently, research on EMS primarily falls into three categories. The first is the rule-based, known for its transparency and robustness, but it has limited performance. The second one is called model-optimized approach. It requires high model accuracy, and it can lead to increased complexity and optimal challenges. Therefore, the third category, named data-driven optimization method, already gained popularity. This method can offer high computational efficiency, and when the model is well trained, it can offer impressive performance. Our research primarily focuses on these data-driven energy management challenges. Specifically, we use deep reinforcement learning method. The main working principle of this method, just shown in the right-hand diagram, involves a training and deployment paradox. During the training, a strategy agent, constrained from the neural networks, interact with the vehicle model and the training conditions. This interaction generates data for training. Once the model is trained, the EMS is deployed in the vehicle for real-world conditions. If the actual conditions closely match the training scenarios, the performance is effective. But there is a caveat, as the performance can diminish in untrained scenario. So for example, let's consider an example from autonomous driving. Just as this GIF shows, a Tesla car uses a trained neural network for object recognition during the autonomous driving, mistakenly identified an overturned truck as a white cloud, and it led to a collision. So this incident exemplified the potential reliability issues of neural network in unfamiliar scenarios. A challenge also present in energy management strategy. In a more abstract view, if we plot different scenarios on the horizontal axis against the performance of strategy on the vertical axis, just as the figure shows in the left side, the rule-based strategy always maintains a constant performance across the scenarios. But the reinforcement learning-based excel in trained scenario. However, the performance will be degraded rapidly in new ones. So therefore, our idea is to identify when the reinforcement learning strategy is underperforming and switch it to the rule-based strategy. In this way, we can enhance the overall system performance, just shown in the graph on the far right. With this motivation, our research approach is as follows. First, we modeled the energy management problem of fuel cell electrical vehicle. Then the main part of our work involves developing our method and energy management strategy. We start with the basic of traditional reinforcement learning-based energy management. Then we introduce our core innovation. The third part involves a knowledge-driven, rule-based strategy to compensate for unreliability in the reinforcement learning approach. Finally, we integrate these steps to form a comprehensive, confidence-aware reinforcement learning energy management strategy. And then we will use the simulation validation to demonstrate the effectiveness of our approach. So let's give some details. In our model, the vehicle has two primary energy sources: a fuel cell engine converting hydrogen into electrical energy, and a lithium-ion battery system. We use the LIB system for short in the following presentation. These systems jointly supply energy to the vehicle. The electrical energy is transmitted via a DC bus to the drive motor, which then powers the vehicle through the transmission shaft. The energy balance, as shown in this formula, is the sum of the power from the LIB and the fuel cell stack adjusted for the efficiency of the DC and AC converters. This output is essentially determined by the driver, making our task in energy management to optimally adjust the power from those two sources for maximal efficiency. Now let's move to the system implementation. The vehicle operates based on a time velocity curve, which is determined the transaction force at any given moment. This force helps calculate the driven motor power, which varies in efficiency at different power levels, just shown in the right diagram. After modeling the drive component, we focus on the energy storage aspects, starting with the fuel cell system. It generates electricity through a mix of hydrogen and air, with efficiency directly linked to its output power. We modeled the fuel cell generator based on the numerical fitting of experimental data. Next, let's examine the other energy storage system, the lithium-ion battery. For accurate modeling, we consider both electrical and aging characteristics. The electrical aspect uses an internal resistor model to calculate voltage and the state of charge changes. Aging is modeled using an ampere-hour throughput model, in which the parameters are derived from experimental data, like the open circuit voltage and internal resistor changes with SOC, just shown in the right diagram. These elements allow us to fully establish the model of the LIB system. With the complete modeling of the system, we now turn to the core of our method. Let's start with the classical reinforcement learning energy management strategy, forming the foundation of our approach. To put it in a simple way, the reinforcement learning aims to optimize its action selection principle, or policy function pi, to achieve the highest possible return R. It uses a value function Q to access the value of taking an action A in any given state S, essentially evaluating the cumulative future impact of an action through a Bellman equation. The goal of this policy function is always to choose the action with the highest value. With defined objectives for both the policy and the value functions, the next step is their implementation. In deep reinforcement learning, we approximate these functions using deep neural networks. It can transfer their objects into neural network loss functions. Through the neural network training, we update the reinforcement learning's policy and value functions. This involves learning from a series of state action reward data groups. A challenge arises when the network encounters states not covered in the training data set. it can lead to a suboptimal performance. So the question then became, how do we identify these low confidence scenarios outside the training site? So our solution is to using a deep ensemble mechanism. We employ multiple independent neural networks to perform the same task. The variance in their outputs measures their confidence level. So for example, with multiple independent networks for the value function Q, we train each with distinct batches from the same database. We use the post-training, in which the variance in response to the same input indicates the uncertainty of the reinforcement learning strategy. And we transfer this uncertainty into a confidence measure, which is inversely proportional to the variance multiplied by the coefficient. So a smaller variance among independent models indicate a higher confidence. We then set a confidence threshold calculated from the average confidence over past time step. So if the confidence for a state action pair is above this threshold, the RL strategy is considered as reliable. So if not, the external assistant may be necessary. For different problems, this external assistant varies. So in energy management, a rule-based strategy suffices. We design a hysteresis controller focused on the battery SOC stability, activating the fuel cell engine to charge the LIB when SOC falls below 40%, and turning it off when it surpasses 60%. The output power of this fuel cell engine is proportionate to the difference between the current and target SOC. It can prevent overcharging or deep discharging of the LIB. While this rule-based approach isn't optimal, it reliably provides enough actions when RL underperforms. So with this, we complete the basic framework of our confidence-aware reinforcement learning strategy. Let's explore the specific RL configuration. The input variables, including battery SOC, vehicle acceleration, and the power and the rate of change of the fuel engine. These variables sufficiently describe the system's current state. The RL output controls the fuel cell engine's power, continuously variables allowing a range of power settings. The reward function aims to minimize the total cost of hydrogen fuel consumption and LIB replacement, which is also incorporate a soft constraint for the battery SOC against a target value. Now let's talk about the validation part. In energy management, vehicle behavior is mainly detected by driving conditions, represented by the time velocity curves. So our RL strategy is trained under specific driving conditions and then tested in others. So we use the real-world driving data for training and two standard cycle conditions for testing. Quantitative difference between the training and the test conditions, including the average speed, speed variance, and the stop frequency, highlight the importance of evaluating RF performance under varying conditions. So regarding our test result, the first question we focus is whether our confidence mechanism accurately reflects RL performance. We examine whether high confidence actions correlated with low energy consumption and vice versa. This training process shows an increasing trend in average rewards, which indicate effective training. Simultaneously, the confidence level, which is shown by the orange curve, also increased, aligning with the performance. This correlation suggests that our confidence metric is a reliable indicator of RL performance. To further validate this assessment, we compared vehicle energy consumption, which is represented by this dark purple bar, and a different confidence threshold setting. So we see that as thresholds increased from left to the right side, the more low confidence actions were excluded, which can result in low energy consumption on the right. This indicates that actions taken with low confidence indeed lead to poor energy performance, confirming the reliability of our confidence metrics as a tool for strategy switching. The next crucial question is how our confidence-based strategy switching mechanism perform compared to the pure RL and rule-based strategies. Focusing first on battery capacity performance, the graph for two test conditions showed SOC changes under different strategy. Our target SOC was 50%, and our strategy maintained it well with our approach and pure RL showing less fluctuation than the pure rule-based. So, which means that our strategy can successfully achieve battery capacity maintenance. Regarding the battery aging cost optimization, our strategy and the pure RL show similar aging, both significantly lower than the pure rule-based approach. This highlights the advantage of RL as an optimization method, which can always offer the better performance. Finally, we come to the most crucial aspect, which is energy consumption. Our strategy shows a 4% improvement in energy performance over the traditional RL and 9.3% over rule-based strategy in test condition 1. And in test condition 2, the advantage increases to about 6.5% over traditional RL and 2.3% over rule-based approach. These comparison results demonstrate the effectiveness of our strategy in different conditions. Interestingly, the substantial scale difference between test condition 2 and the training condition, as shown in the right side semi-transparent graph, which highlights the classic deep RL energy management strategy may not always outperform rule-based strategy, especially in scenarios vastly different from the training condition. So this is the key point of our study. The minimal advantage of our strategy over the pure RL and in the training condition indicate that confidence mechanism is less pronounced in well-trained scenarios. However, its benefits became significant in untrained conditions, just as shown in the left and the middle comparisons. To further illustrate this difference, we test the strategy with vehicle mass halved or double from the training condition. We find that the traditional RL performed better than the rule-based in the baseline case, but was outperformed under changed mass conditions. Importantly, our strategy maintained the best energy performance across all test conditions. Lastly, we assess the computational complexity of our strategy, which involves multiple model ensembles. Comparing the CPU time per step, our strategy's computational load is only slightly higher than the traditional RL, with millisecond level processing times, which can well meet in the real-time vehicle operation requirements, which means that our approach is also highly efficient computationally. So let's go to the conclusion part. In summary, we introduce a novel confidence-aware reinforcement learning method to enhance the performance of RL-based energy management strategy for electrified vehicle, especially in untrained scenario. Our confidence-aware mechanism based on the deep model ensemble demonstrate a 4% improvement in vehicle energy efficiency without compromising other optimization objects. So that's the end of my presentation. Thank you, and my team and I are happy to answer any questions.